Hi, this is a presentation of our assignment, which module is Process Control and Instrumentation. Today we are going to talk about the process control in the beer production. In other words, it's also called as brewing process. The brewing process has taken place since around 6 millennium BC. The archaeologists has the evidence proof that there is an emerging civilization include ancient Egypt and Mesopotamia brewed beer. In the past, the ancients used malted barley and cereal grains as their fermentable starch source. They kept stepping on those starch until it became muddy, and after that, store in the tank and let it undergo fermentation with yeast. These days, there are several steps in industrial brewing process which include milling, crush the malt in order to extract fermentable sugars, mashing, use natural enzymes to break malt starch down into sugar, then come to lautering, separate wort and husk, and boil the wort while adding hops. After that, wort separation and cooling, then come to fermenting, conditioning, filtering, and last step, packaging. This is brewing process flow diagram. All the steps I have mentioned in the previous slide. Here shows the difference between PFD and PNID. This one is showing a simplified process flow diagram from boiling to fermenting. This is process and instrumentation diagram. This fig shows a lot of valves and variables controlled within the process flow. The label with V is valve, the label with PC, this one is pressure control, and the label is LC is the level control, and the last one is a TC, the temperature control. There is a heat exchanger in the middle of way of whirlpool, filter, and fermenter. The control system that used in fermentation process is PLC-based control system. It has many outputs and inputs to connect to the P controller and process tank. The heat exchanger is used as a control unit on fermenter. After that, we'll show you the control flow diagram and the transfer function of each block for the temperature control. The upper left picture shows the control of pH in fermenter. The attached sensor will send the arrow to the transmitter. After a controller receives the signal from transmitter, the valve of manipulated input, which is the reagent, is controlled to open or close. The other two pictures is the temperature control. The PT100 and the probe are the sensor also, and will send the signal to control through transmitter to control the hot or cold water to get in the jacket of the fermenter.
We are going to look about the major equipment in the fermentation process. This process is the most important part in the process where the alcohol is formed at this step. As shown in the diagram, the fermenter has its inlet where the cereal grain, yeast, and nutrients are flowing in. The aerator is where the oxygen flows in for the yeast respiration, and the yeast respiration will then convert glucose into alcohol and carbon dioxide. To avoid the accumulation of the carbon dioxide building up in the system, so there is a exhaust outlet will be installed to remove the carbon dioxide. Furthermore, the stirring paddle is used to create a uniform mixture and accelerate the fermentation process. Other than that, a series of probes that have different functions are installed to monitor the pH level, oxygen level, and the heat, which is the temperature, and so on in the system. Heat jacket is used to control the temperature at different type of alcoholic beverage. They will have different brewing temperature. The reaction in the fermenter is denoted like that. Glucose, under the existence of yeast, will then be converted into ethanol and carbon dioxide. So there are two types of fermenter available. One is batch fermenter and the other one is called continuous fermenter. So for batch fermenter, all the materials are poured into the system at one time and extracted after a certain time. Hence, the microbes in the reactor will then go through all the phases like lag phase, exponential phase, stationary phase, and dead phase. Next, continuous fermenter. The microbe growth in this continuous fermentation process will be maintained at the exponential phase, and all the product form will be extracted continuously. So for large-scale production, however, batch reactor is more favored. Now we talk about the block diagram in controlling the temperature of the fermenter in a fermentation process. There's a PI controller will be proposed at GC, and the output of the controller will then make a change at the valve, which is denoted as GV. And GP is the process of heat exchanger with a time delay. The temperature in the system is monitored by probes that we shown just now in the fermenter, which is GM. It is to detect any disturbance change and report any error signal to the controller for making change. The block diagram will be discussed furthermore in the coming slide.
The manipulated variable is the valve for input and output of hot and cool water. The control variables will be the temperature, and last, the disturbance will be the ambient air temperature and the steam leakage. We are now focusing on the temperature control, and we will continue to see how it works.
The block diagram for our process is in the form of a control loop. The transfer function of our valve is 0.13 over 3s plus 1. Our process is in the form of a first order plus date time, which is 50 e negative s over 30s plus 1. The transmitter 0.16 over 10s plus 1, and the disturbance 1 over 10s plus 1. A P-only controller was proposed which has Kc value of 23.8. Stability is an important factor in a system. We are going to use the Wolf stability criterion to determine whether our system is stable. A system is said to be stable if the output response of the system is bounded for all bounded inputs. A bounded input is an input that stays within the upper and lower limits for all values of time. For example, the system of y equals to sine x is stable because it is bounded, while the system of y equals to x is unstable because it is unbounded. The stability of a system is very important. We are going to use the Wolf stability criterion to determine whether our system is stable. Stability criterion is based on the characteristic equation 1 plus GOL, which can be expanded into this form. The first criterion is that all coefficients has to be positive, and if one of them is negative or 0, then the system is unstable. We have to construct the roof array for the system. The first two rows are the coefficients in the characteristic equation, and the other elements are obtained by cross multiplication. The second criterion is that all the elements in the leftmost column have to be positive for the system to be stable. A P-only controller was proposed with Kc value of 23.8 is used. Therefore, we are going to calculate whether this is stable. The range of values at which Kc is stable, we first set Kc to be an unknown. The characteristic equation is expanded into this, and we construct the roof array to be like this. Using the formulas on the left hand side, we calculate the values of B1, B2, C1, and C2. The theory is that all elements on the leftmost column have to be positive. Therefore, in order for B1, C1, and B2 be positive, Kc must be within this range. And since the proposed value of Kc is outside of this range, the system is unstable. As our system is unstable, we are going to calculate new values for our controller. The Bode stability criterion theory is used to calculate our new values for our controller. To obtain the ultimate gain, we first calculate the ultimate frequency. Setting the phase angle as negative pi, we obtain the ultimate frequency of this. Then, the ultimate period is obtained from the ultimate frequency by using this formula. After getting the value of the ultimate frequency, we set the amplitude ratio to be equal to 1 and obtain the ultimate gain of this value. To obtain the settings for the controller, we use the Zn method. Formulas listed in this table, we obtain the values of Kc, Ti, and Td. After plugging in the values into the general equation of the controller, we finally obtain the transfer function of this.
The stability of a control system is defined as the ability of any system to provide a bounded output when a bounded input is applied to it. Stability is considered to be an important property of a control system. It is also referred as the system's ability to reach the steady state. The performance of the control system is highly dependent on the stability of the control system. A system is said to be stable if its output is under control. A stable system produces a bounded output for a given bounded input, and there are three types of system based on stability. An absolutely stable system is the one that provides bounded output even for the variation in the parameters of the system. This means it is such a system whose output after reaching a steady state does not show changes irrespective of the disturbance or variation in the system's parameter values. A conditionally stable system gives bounded output for the only specific conditions of the system that is defined by the parameter of the system. Thus, we can see here the system exhibits stability only under particular condition, and if that particular condition is violated, then the system generates unbounded output. A marginally stable system is the one that generates a signal which is oscillating with constant frequency and amplitude when a bounded input is provided to it. These oscillations are known as sustained oscillations. Why use PID controller compared to P controller? So the working principle behind a PID controller is that the proportional, integral, and derivative terms of PID must be individually adjusted or tuned. Based on the difference between these values, a correction factor is calculated and applied to the input. Proportional tuning, or P, involves correcting a target proportional to the difference. Thus, the target value is never achieved because as the difference approaches zero, so too does the applied correction. Integral tuning, or I, attempts to remedy this by effectively cumulating the error result from the P action to increase the correction factor. Derivative tuning, or D, attempts to minimize its overshoot by slowing the correction factor applied as the target is approached. So to summarize this slide, P controller can only stabilize first-order unstable processes, and by first-order processes, it means processes with one energy storage. For PID controller, it can stabilize higher-order processes that are unstable, and PID controller is the most commonly used controller design in the industry. For the P-only controller, when Kc equals 23.8, it shows that the system is unstable. Then after changing into PID using ZN method, the system becomes stable, and as you can see, there is less overshoot and the ultimate value is reached even faster. Thank you.
So I will talk about the process control strategies proposal. As shown in the slide, this is the original design of the reactor. This is the reactor design from a winter and relatively low temperature country, so it will have heating process even though the fermentation is an exothermic reaction. This is our proposed reactor design, and we will gonna talk about it to reach it step by step. So firstly, an electric motor stirrer should be added to the fermenter. This allows the temperature of reactant can be distributed evenly in the reactor. The stirrer will be either at certain RPM. The blade should be designed to pull the reactant from top to bottom, forming a convection in the reactor. The second strategy is the steam heater should be converted into electrical heater, because the electrical heater allows a more accurate temperature control on the reactant. So for an example, if heating had to be stopped, electrical heater will directly shut off while steam heater will still heating up the reactant because of the hot steam, which after the war, before the heat exchanger will still supply a very small heat to heat exchanger. This causing steam heater required longer time to stop the heating process. For the third strategy, two new temperature process control are proposed to be added as shown in the figure. So for the controller to stirrer, the process block diagram was shown as on the screen. The purpose is to let the stirrer spin faster when the electrical heater on. If the stirrer doesn't spin faster, the big power electrical heater may heat up the reactor surrounding it very fast and possible to kill all the organisms, denature all the enzyme around it, and causing the chemical changes on the reactor, which will cause the unpredicted change of taste of the beer, maybe sweeter or bitter. For the thermostat controller to stirrer, the block diagram was shown on the screen. The purpose is to let the stirrer spin faster if the temperature at top too low. Now the screen shown an illustration of heat in the reactor when the case of stirrer spins too slowly. This is to prevent the case of heat accumulated at bottom of reactor while the heat at top of reactor not enough. The optimum temperature for fermentation is 32 to 35 degrees Celsius, which means we need a set point of 33.5 degrees Celsius, allowing an error of 4.2857%. For the fourth strategy, we will make insulator thicker. This is to lower the heat loss and make the temperature rises and drops becomes lower. This allows the controller to control the temperature easier to become more accurate. Lastly, we make the reactor become oval shaped as shown in the screen. This is for a smoother convection. This is the end of my presentation. Thank you.
It comes to the end of the presentation, and thank you for your attention.